This is the chapter which discuss about this is the chapter which discuss about how what is the relationship between the electricity and chemistry. Here we have two important topics that are how electrical energy how electrical energy can be converted into chemical energy, and the next topic is how chemical energy can be converted into electrical energy. This the conversion of electrical energy to convert chemical energy. This can be done by chemical reaction, and here also chemical energy to electric energy is also uh, done by a chemical reaction, and the equipments and the device which are used for the conversion of equipments and devices which are used for the conversion of electrical energy to chemical energy are said to be electrolytic cells, and the devices which are used for the conversion of chemical energy to electrical energy are said to be galvanic cells. Now, in this chapter, at the beginning, we have to know some of the terms which are very important, such as electrodes, next, electrolytic solution, and external source. What are electrodes? What are electrodes? The electrodes are the rods which are dipped in the electrolytic solution. See here two kinds of rods are there. One rod is connected to the positive terminal of the battery, and while the next rod is connected to the negative terminal of the battery. The rod which is connected to the positive terminal of the battery is said to be anode, and the rod which is connected to the negative terminal of the battery is said to be cathode. And the electrolytic solution. Now, in the electrolytic solution, this is the solution containing cations and anions which conducts electricity in the solution. A solution containing cations and anions which conducts electricity are said to be electrolytic solutions. Basically, we are ionic solutions when dissolved in the polar solvent conducts electricity, and this kind of substances electro solutions are said to be electrolytic solution. You can take an example as sodium chloride dissolved in the water, common salt solution. Okay, the next important uh, term is the external battery or the external source. In the electrolytic cell, we are using an external source which is used to supply the energy in the electrolytic cell. By using the electrolytic external source, we are supplying the energy into the electrolytic cell, and that is electrical energy is supplied to accomplish the reaction. Whereas in the galvanic cell, we are using a voltmeter instead of external source. Here, why we are using the voltmeter means here voltmeter detects the whether the current is flowing or not. Okay, now next. Next, electrical conductance of aqueous solution of the electrolytes depends on. Now see here, electrolytic solution. Electrolytes are nothing but electrolytic solution. The conductance of the electricity in the electrolytic solution depends on the following factors. First factor is nature of electrolyte. Nature of electrolyte means what type of substances solute is dissolved in the electrolytic solution. If we are taking the ionic solvents, if you are taking the ionic substances as solute in the polar solvent, then the whatever the electrolytic solution is formed, that will conduct the electricity to a greater extent. If suppose if you are adding non-polar covalent molecules, CCl4 or any other molecules in the electrolytic in the solvent, then such type of substances unable to get dissociate into the respective ions, so they doesn't conduct the electricity. So here the nature of electrolyte means here especially the ionic substances when dissolved in the electrolytic solution conducts electricity to a greater extent. The next is polar molecules dissolved in the electrolytic solution conducts electricity, but non-polar molecules unable to conduct the electricity. Next is concentration of electrolyte. Concentration of electrolyte, what means here, with the increase of concentration, resistance increases for the conductance of electricity. So with the decrease of concentration, that is increase in dilution, favors the conduction of the electricity. Next is temperature effect. With increase of temperature, conductance of electricity favors. So with increase in temperature, conductance in the electrolytic solution increases. The next point is nature and viscosity of the solvent. Nature, what kind of solvents we have to take? Polar solvents. So just means here polar solvents, water is a polar solvent which supports the conductance of electricity, and with increase in viscosity of the solvent, the conductance of electricity decreases. The next factor is size and solvation of ions formed in the dissociation of electrolyte. Now, let us consider a running competition between a fat person and a slim, running competition between a fat person and slim and energetic person. We know that slim and energetic person can run fast compared to a fat person. Means here mobility of movements is inversely proportional to mass or size. When the size is decreasing, movement increases. Similar effect can be observed in the ions also. The smaller the ion, more is the mobility, higher is the mobility of ions. So high will be the conductance of electricity with the decrease in size of the ion. And next is solvation effect. The solvation effect is ions are getting ions attracts the solvent molecules due to their charge. You can see here Na plus ion attracts the water molecules because Na plus ion it attracts the polar covalent molecule favoring oxygen comes close to the Na plus ion. Similarly here Cl minus Cl minus ion attracts the water molecules preferring hydrogen come close to the Cl minus ion. This effect attract ions attracting the water solvent molecules is said to be solvation effect. With increase in solvation of ions, the conductance decreases. Okay, the next is Faraday's first law. Faraday's first law. Now, what is the Faraday's first law? Now, see here, when you are supplying the electricity, by use of external source, what is happening? What is happening when you are supplying the electricity through this external source? The cations come close to the anode. Cations come close to the cathode, and anions move towards the anode. And at the anode, oxidation reactions take place. That is, Cl minus ions loses electrons and get neutralized and evolving Cl2 gas. Similarly, cations when come close to the cathode gains electrons and get neutralized and get deposited on the electrode, that is cathode. That is what he is saying means Faraday's the mass of the element liberated on an electrode during the electrolysis is directly proportional to the quantity of electricity Q which passes through the solution of an electrolyte. Means what is that? When you are supplying the electricity, more the quantity of electricity is supplied, more is the higher the amount of substance liberated, that is Cl2 gas liberated, or more the higher the amount of substance, that is metals deposits at the electrodes. If you are supplying the more electricity, more is the substance evolved or liberated or evolved or deposited at the electrodes, corresponding electrodes. That is, here if m is the mass and amount of the substance deposited or liberated at C is the current in amperes which passes through the time t seconds, then according to this law, that here we have to take I am taking the I, this should be C. According to this law, amount of substance is directly proportional to amount of substance deposited at the electrode is directly proportional to current supplied, where E by 96500 is a proportionality constant, and this is nothing but chemical equivalence. Here we have two diagrams, one diagram showing that what type of process is taking place, and here this by use of these diagrams showing the when external source is applied, ions get close, means positively charged ion electrode is there here. For positively charged electrode, that is anode, attracts the negatively charged ions, red color balls, and cathode attracts the positively charged cation, and get neutralized here. Okay, the next, based on Faraday's law, let us do one problem. This is very important with respect to IP. A solution of copper sulfate is electrolyzed for 10 minutes. A current 10 minutes with a current of 1.5 amperes. What is the mass of copper deposited at the electrode? What is the mass of substance copper deposited at the electrode? According to the Faraday's first law, we know that M is equal to ECT by F, where F is nothing but 1 Faraday. 1 Faraday is the charge carried by 1 mole of electrons. In 1 mole, Avogadro number of electrons is present. So, yeah, Faraday is nothing but charge carried by Avogadro number of electrons. So, Avogadro number here is 6.023 into 10 to the power 23 multiplied with charge on each electron is 1.6 into 10 to the power minus 19. On multiplying, we are getting the 1 Faraday value as 96500 coulombs. Now, next, M is equal to ECT by F. And values are given here. C is the current supplied through the external source. C is the time for which it is supplied. For 10 minutes means 10 minutes into multiplied with 60 seconds, 600 seconds. And E is equivalent weight. Here equivalent weight is equivalent weight of the metal, atomic mass of the metal divided by charge on the cation. It can be charge on the cation or number of electrons passed in the redox reaction. It can also be number of electrons involved in the redox reaction or charge on the cation. That is, here is for atomic number of the copper is 63 and the charge is copper is plus 2 charge. So 63 by 2 is the equivalent weight of the copper. Now, substituting the values in the equation, M equal to ECT by F. 63 by 2 multiplied by 1.5 amperes 600 seconds divided by 96500 and you will be getting the result as 0.293 grams. Okay, this is a very important answer, very important problem with respect to IP. Now, the next is Faraday's second law. Now, see here, according to Faraday's first law, amount of substance deposited at the respective electrodes is directly proportional to the amount of current supplied or charge supplied through the electrolytic solution. Suppose here we are keeping the same amount of charge is supplied through the different kinds of electrolytic solutions. Same amount of charge is supplied. Now see here, three kinds of electrolytic cells are there, but we are using the same external battery. That is, we are supplying the same amount of charge in the three different electrolytic cells. Then what happens? This will be discussed in the Faraday's second law. The Faraday's second law states that when same quantity of electricity passes through the solution of different electrolytes, then the amount of substance liberated at the electrodes is directly proportional to their chemical equivalence. It's directly proportional to them. Chemical equivalence. Chemical equivalence, it depends on the nature of the substance which is dissolved in the solution. That is, chemical equivalence depends on the nature of the substance. So, chemical equivalence, the amount of substance deposited at the respective electrodes is directly proportional to chemical equivalence. So, from this statement, we are getting the relationship as m1 by m2 is equal to m e1 by e2, since the same amount of charge is supplied through different kinds of electrolytic solutions. Okay, we are getting the relationship. Amount of substance liberated at the electrode directly proportional to chemical equivalence. Now next, Kohlrausch's law. See here, Kohlrausch's law. This states that limiting molar limiting molar of an electrolytic solution represented as individual contribution of molar conductivities of anion and cation of electrolyte. Anion and limiting, it is a what? See here. This states that limiting molar conductivity of an electrolyte represents as individual contribution of, that is individual means it can be sum of individual contribution of molar conductivities of anion and cation of an electrolyte. First, we have to know what is the limiting molar conductivity. Limiting molar conductivity is nothing but the molar conductivity at infinite dilution. We can, I will give you the example that suppose 1 mole of substance is dissolved in the water present in the swimming pool. Then in this, whatever the water, the quantity of water taken in the swimming pool, that will be very high compared to solute dissolved. That is, we are dissolving only 1 mole in the enormous amount of water. Then it will be a dilution to a infinity level, that is called as limiting molar conductivity. Limiting molar conductivity. Then what happens actually is, when you are diluting to a infinite level, then what happens, whatever the ions present in the solute get dissociated completely. So limiting molar conductivity at that time, the conductivity shown by the conductivity shown by the electrolytic solution is the sum of the molar conductivities of anion and cation of the electrolyte. Now next, applications of Kohlrausch's law. First application, determination of equivalent conductance for weak electrolyte. Determination for equivalent conductance for weak electrolyte. See here, this is the weak electrolyte. Weak electrolytes are the substances which does not get dissociated completely are said to be weak electrolytes. And the strong electrolytes are the substances which get dissociated completely or easily are said to be strong electrolytes. Examples for the strong electrolytes are ionic molecules, NaCl, and next is potassium chloride, potassium sulfate. Get dissolves, when it get dissolved in the water, get dissociates completely, leading to the formation of ions. And even strong acids and strong bases also get dissolved to a greater extent. So strong acids, strong bases, and salts formed by strong acid and strong bases are said to be considered to be strong electrolytes, whereas the salts or salts formed by weak acid and weak base are considered to be weak electrolytes. Now, and weak electrolytes are nothing but, here we can take weak acids, weak bases also comes under the weak electrolytes. For that, equivalent conductance for the weak electrolytes can be calculated by use of Kohlrausch law. Kohlrausch law is applicable for the determination of molar conductivity of weak electrolyte. It cannot be directly determined by extrapolation method. For strong electrolytes can be conductivity of strong electrolyte can be determined by extrapolation method. For weak electrolyte, we can't use this method. So here Kohlrausch law is applicable. Now, according to this law, limiting molar conductivity is the sum of limiting molar conductivity of anion and cation of the electrolyte. That is, limiting molar conductivity of the acetic acid is the conductivity shown by is the sum of the conductivity shown by acetate ion and H plus ion. Okay. Now, the same thing. According to this law, limiting molar conductivity is the sum of the values of sum of the equivalent conductivity values of anion and cation of the electrolyte. Now, for the acetic acid solution, molar conductivity is given as that is here CH3COOH is equal to lambda naught CH3CO minus plus lambda naught H plus. Lambda naught CH3COH can be equal to lambda naught CH3COONA plus lambda naught HCl minus lambda naught NaCl. Applying the Kohlrausch law here, according to Kohlrausch law, CH3COONA can be written as CH3COO minus plus lambda naught Na plus, and here lambda naught H plus and lambda naught Cl minus. Now next is lambda naught Na plus and lambda naught Cl minus. Now when you are applying the Kohlrausch law, by using of Kohlrausch law, applying simple mathematics here, this one Na plus and Na minus, lambda naught Na plus and lambda naught Na plus get cancels here, and this one and this one get cancelled here. Okay, and we'll be getting the answer as lambda naught CH3COO minus plus lambda naught H plus. The next is next application of Kohlrausch law is no. Here we have given you one a problem here. Calculate the lambda naught for calcium chloride and MgCl2, given that lambda naught values for the following ions. Now here lambda naught values for calcium ion and Mg2 plus ion, Cl minus ion and sulfate ion are given as follows. Now here first problem, calcium chloride. According to the Kohlrausch law, lambda naught CaCl2 can be given as lambda naught Ca2 plus and plus 2 lambda naught Cl minus, according to the Kohlrausch law. Applying the values which are given here, just substitute the values and get the answer. Next is calculation of lambda naught MgSO4 value. That is here lambda naught Mg2 plus value is this much. We have to substitute here, and lambda naught sulfate ion value is here. We have to substitute the values and get the answer. The answer is like this. Okay. Next. The next application is the lambda naught values for NaCl, HCl, sodium acetate are given as 126.4, 425.9 and 91.0 S centimeter square per mole respectively. Then calculate the lambda naught value for HAC, that is so acetic acid. Let us calculate the lambda naught value for HAC, that is acetic acid. According to the Kohlrausch law applying here, it is equal to lambda naught H plus and lambda naught AC. Here we are applying the Kohlrausch law formula here. Lambda naught HCl, lambda naught value of sodium acetate, and lambda naught value of NaCl. Substitute this one. The explanation I have given, we have discussed earlier. Now substitute the answer, substitute the values and get the answer. The next one, application of Kohlrausch law. The next application of Kohlrausch law is calculation of dissociation of weak electrolyte. First application is to calculate the conductance of weak electrolyte. The next application is to calculate the dissociation of weak electrolytes. The degree of dissociation, in that one we have degree of dissociation and dissociation constant. Degree of dissociation is the ratio of molar conductivity to the limiting molar conductivity. That is, degree of dissociation is represented by alpha lambda naught m by lambda naught